Okay, so you can see the first part of the code here. The upper part I have discussed already with you on Newton-Raphson method. I think it is visible to you here. So this part of the lecture, I'm just giving you an idea of vectors. So see this part, import numpy is np. Okay, you have to always do that if you are on Colab. If you have installed Python, then it's fine. But if you are on Colab, you have to import numpy every time. Okay, now and then. So I'm creating a row vector over here. You can see I'm creating a row vector over here. How the row vector looks? 1, -5, 3, 2, 4. These are the elements of the row vector. And vector column is the column vector. Okay. So what I do here, I'm printing vector row. What is the shape? Like what is the size of this vector? Okay. So if you see carefully, like the vector row has how many elements? 5 elements, and it is stored in one row. So one row and 5 columns. So you can see, if you want to extract the shape of that vector, so you can use the shape function. So the name of the vector dot shape. That means you are trying to access the shape attribute of that vector. Okay, so you can see when you do this vector row dot shape, then it is giving you one row and 5 columns. Okay. When you do vector column is empty dot array, this thing, you can see how the first one and the second one are different. It's all in terms of the bracketing. So in Python, I would strongly suggest that you please be very careful with the indentations. Okay. Write an if statement, then you should follow the indentation that the other statement inside the if should follow a particular pattern line by line. Okay, if it doesn't follow, Python will throw an error. Okay, so indentations, please be careful in Python. Even if the code is correct, everything is correct. If the indentation is not in the lining, the alignment is not correct, then it will throw error. Okay. Yes, these things like I will not discuss here. These things I will tell you more about it. What is list of list? Okay, what is list of list? Okay, there you will learn all about this. What happens if you put like double columns, like double brackets? So, want to create an array and then you can take the transpose. Yes, that can also work. Yes. So what he was suggesting is vector column. Why it appears a bit complicated? Instead of that, he was suggesting not reshape. Okay. So yeah, there is something known as reshape function also. Okay. So these all things I hope that you will be to Python course. Okay. So I hope that these will be covered in that. And also in data analytics, I think in data analytics course, I think basics of Python should have been done in the first class, isn't it? Yeah. So in those cases, you will be seeing list of list, array, how to store names and all in that. Okay. So start from basics. Whatever code I am giving to you, don't just copy paste it. Write about it. Like if you see the code running, type it on your own. Don't copy paste. Type on your own. Okay. Let us see. Yeah, then I think this is the mostly regarding the bridge course I taught you about. Bridge course I taught you about. So this is regarding the norm. Okay. So if you have a vector, then what are the different kinds of norm to the vector? In the bridge course, the first class I told you about L1 norm, L2 norm, L infinity norm. Okay. So these are just I am trying to show that these are already there in Python. Okay. So how you can compute this? Just you need to write the norm and the vector comma 1. That means it's L1 norm. If you write norm, the name of the vector comma 2, then it is L1 norm, sorry, L2 norm. If you want to consider L infinity norm, then norm, the vector name comma np.inf, short form for infinity, np.inf. So that will give you the 3 different kind of norms. Now you can ask why we need these three different kind of norms. You need these three different kind of norms depending on your application. Okay, if you are trying to consider distance, then you can try to use the L2. Okay, depends on the space you are in and all this in your applications. Sometimes you want to know the maximum element in your array or in your vector. There you can just use the L infinity norm. So you can see the vector I am trying to assign is vector row dot t, that is transpose. So let us come back to that equation. This was the row vector 1 minus 5 transformed into a column vector. Okay, so you can see 1 minus 5, 3, 2, 4 are all in column mode. They are all column vectors. Okay, there is a single column vector with rows in the column. Like each row has a new element. L1 norm, you can see what is the definition of L1 norm. L2 norm, what is the definition? But L3 norm you can easily see. L3 norm is just the maximum of the magnitude of the vector elements. So what's the maximum in these elements? If you take the magnitude 5, if you take the magnitude minus 5 of magnitude, that is 5. Okay, that absolute value, max of the absolute value of the elements. Can you appreciate it? So L infinity norm doesn't require any sort of calculation, just it will be one of the elements of your vector, just one of the elements of your vector. But L1 and L2 norms, you have to do some computation which Python is doing for you. Yeah, so yes, this I don't want to cover. Yeah, we can cover actually. So you can see this is the definition for the cross product. Sorry, the dot product. You know the dot product of two vectors, isn't it? Are you aware of the dot product of two vectors? Yes? No? Yes. So if the two vectors are perpendicular, what is the dot product? 0. Okay. If two vectors are parallel, what is their cross product? 0. Okay. You know the dot product of two vectors v and w can be just written as dot product of two vectors can be written as like v and w, suppose, is the magnitude of v vector, magnitude of w, cos theta, the angle between the vectors. So if since the cos is involved, if the vectors are perpendicular, cos 90. So therefore, if two vectors are perpendicular, the dot product will be 0. Okay. So you can see that's what we are doing here. And now you might be wondering why we need it. Hold on, we will see where we need it. Then the dot. Okay. Dot means it will take the dot product between the two vectors. Okay. So here are the two vectors v and w, the two row vectors. And what I'm doing here, I'm trying to find the vectors. So how can you do? You know already cos theta. I think I need to write this. It might be tricky to understand. Yes. What I'm trying to do is the two vectors are there, v and w. I'm trying to take the dot product of them. How you will take? You need to take the magnitude of them, multiply them together, and then consider the cos of the angle. This is the angle between v and w. Fine. Now I am trying to get the angle behind this. How I can get the angle? That means I need theta, right? So you can make cos theta your subject. V bar dot w bar divided by norm of v times norm of w, right? How can you write theta? Yes, cos inverse of v bar dot w bar divided by norm of v divided into norm of w. The same thing we are doing here in the coding part. Okay. If we return to our coding, okay, can you see it again that these are the two vectors v and w, row vectors. I am taking the arc cos. That means it's just like cos inverse. Okay, arc cos. Dot product of v and w transpose. All right, v and w transpose. So you have to take this account into the size of the two vectors. Okay. Norm of w. So that just gives you the angle over here. Okay. So this is just slow, like easiest interpretations of dot and cross product, which might come in the course. So I am just telling you here. Okay. Same thing you can do for cross product. Nothing else. Cross. Okay. Same you can do with np dot dot. Okay. This does the cross product between the two vectors. Okay with you? So just you are using the cross function, nothing else. Already it is in Python. You don't have to define the cross product as the norm of the vector 1, norm of vector 2 into sine of the angle of the vectors. No, already there. So just give the vectors, it will automatically compute the cross product. Then in the morning class, I discussed something regarding the linear combination, isn't it? Linear combination of vectors. So here I am trying to consider the linear combination of three vectors. V, W, and U. So V, W, and U are defined like this. You can use your own numbers. I have used these numbers. You can take 3 times V minus 2 times W plus 4 times U. Okay, are you feeling comfortable that this is the linear combination of V, U, and W? Yes. Is this a linear combination of V, U, and W? What do you think? Yes, because these are just constant multiplied by that vector and adding them together. There is no V square involved, right? There is no U square, VW, something like that involved. So it's a linear factor. So this is a linear combination. So I am trying to show to you that this linear combination, that is this vector minus 8, minus 1, 4, can be written as a linear combination of V, W, and U. So what can you say from this? Vector X, which is this, is linearly dependent on the vectors V. It's not linearly independent, right? If it is linearly independent, you cannot write them as a linear combination of the vectors. Okay? Is it clear? Okay. So this is something which we did not cover in the class today, but these are very basics. How to compute determinant of a matrix, how to find inverse of a matrix. Okay. So I'm just covering them just so that it is not confusing to you when you see them at a bigger stage. Okay. So suppose this is a matrix. Then now let us. So I'm giving you different examples. So the small examples we are just looking at. So this is one matrix M. You can see it. So how many rows it has? Yes. And 4 columns. Yes. So it's a square matrix. It's a square matrix. Now he's saying me use the np dot I. If you use np dot I function, it will create an identity matrix, okay, with all diagonals 1 and other elements 0. Okay. So use this function np dot I to produce this 4 cross 4 identity matrix. Fine. Multiply m by I and show that the result is still m. Okay. You already know when you multiply the matrix with an identity matrix, it is written in the same matrix, right? How many of you are saying yes? If I multiply a matrix M with an identity matrix, we will again get that same matrix back. How many of you are saying yes? Or no, it is wrong? Yes, it is true. Okay. So that's the basic property of the matrices. So here I have constructed that matrix np dot array with element written down over here, each vector. Okay. Fine. And it is printing that. If you write print M as this, and it is printing it here. It is printing it here. Okay. Then I am also interested in finding the determinant of M. Okay. See, you have to know also the matrix has 0 determinant or not. In the morning class, I told you about that. If determinant of a matrix is 0, it is it cannot be inverted. It is not an invertible matrix. And also I told you that sometimes we call it to be a singular matrix. Singular matrix also. Okay. And I also told you why inverse of a matrix cannot exist if determinant of A is 0, because in 2 by 2 case you do inverse to be 1 by determinant of A into adjoint of A, right? So then it is not defined. Yes. So just think about this. So what I do, I create an identity matrix over here, np dot I 4. That means it will create automatically a 4 cross 4 identity matrix with all diagonal elements 1, others 0. Okay. All right. So then what I'm doing here, dot m comma I. Okay. So you can see the same result over here. You can see here like m and m star I is the same. Of course, one dot means it's 1.0, okay, the float. But you can see that those two are matching. So this is just an idea for you to show how to multiply those two matrices. Okay. Is it fine? Fine. Hmm? Okay. So what we just encountered in the previous example is the matrix M, which is defined as this quantity over here, 4 cross 4, has a determinant of minus 38. It has a determinant of minus 38. So it is not equal to 0. That means it is invertible. It is invertible. Now, he is asking in the next example that the matrix M in your previous example had a non-zero determinant. Okay. Then you can, of course, compute the inverse of M. Okay. Show that the matrix this has a determinant value of 0 and therefore has no inverse. So questions in the same. Okay. So our job is to calculate the inverse of the matrix M. First of all, let us solve this, then we'll look into other case. So nothing else, just use the inv function. Inv bracket the matrix name. Okay. You can just like import inv every time you have to do import for this info lab. Okay, and you are importing not from numpy this time. Okay, you are importing from the package numpy.linalg, linear algebra package. Okay, linear algebra package inv function from there. So you can see inv comma inv bracket m. So it is computing, it will give you the output will be the inverse of the matrix M. You don't need to do anything else. So these are the examples where if you just want your inverse of a matrix and some calculations, in some computations, then you can just use this inv function. Okay. Hmm? And he told that yes, take this matrix P, which is written over here, 0, 1, 0, 1, 0, 1. Okay, what is the determinant? Without computing, without giving the computer also, you can answer this. Okay, why? Because in this matrix P, can you carefully see this matrix P and why say to me that suddenly, without even giving to the computer, you can find the determinant just by eyeballing, just by looking into it, you can find the determinant to be 0. You can find. Why? Hmm? Tell wrong, let it be wrong. She was telling the answer, then she was not telling. Second row is 0. Yeah, you already know, but you did not, we're not telling again. You should not have fear in telling the answer. Let it be wrong. I won't scold. In this quarter, I am not. Since 3 classes, do you think I am that kind of? Already had 3. How many classes? 4 class. Okay. Third class. Since 3 class, 4 hours, 12 hours you spent in the class. Do you think that I ever said that wrong means why and no? I feel like that. So if you open up, it is a good thing because then you will be learning more efficiently. Okay, so this is the inverse of m, a hugely complicated one. Okay, with many decimal places. Fine, inverse of m. You did not do. Did you? You did not do anything, right? Computer did all the things. So this is the advantage of this. Suppose you are being given a very big matrix to do, then how Python is computing the inverse? Okay, you should be asking like how just by writing inv and a matrix, Python is able to compute the inverse. Okay, so Python is using some inbuilt method which you class. Okay, I will show you. I'll show you. I'll show you. So determinant of P is 0. Fine. Why? Because you see one of the row of the matrix P is 0 totally 0. Okay. So if any row of a matrix is 0, determinant is always 0. Any column determinant is already 0. Why? Because determinant of A you can transpose is again, and determinant of A is same as determinant of A transpose. Okay. So these are just a bit of basic linear algebra. It is okay if you don't get all the things in this class, but it is important that it is not important that you understand everything here in this class. But it is important that after you go through this class, you see to this again and again. That is important. Okay. Right. So yes. So in the class also we learned about something known as a condition number, isn't it? Condition number of a matrix. Let us see. Hmm, something we discovered regarding condition number. So you can see over here, the condition number is a measure of how ill-conditioned that matrix is. Okay, and then we talked about in the morning that it is defined as the norm of A times the norm of the matrix inverse. Okay, now we will see in Python how you can compute the condition number for a given matrix. Okay. All right. So you can see here, like this is the matrix we are taking A matrix. I am importing COND. Okay. From from interesting. Okay, so you have the matrix A over here. Okay, and I am importing COND and matrix rank. Rank of a matrix I will not define. I will define in the next class. Okay, but don't worry about it. So this is the matrix A for you. And just if you want the condition number of the matrix COND A, nothing else. So it is giving you 4.04 something. What does this mean? What does this mean? That let it be a suspense. Next class we'll uncover what is it mean. Condition number is a real number. Anyway, you got an idea how it looks. But what it interprets, what it gives, of course, it gives you how ill-conditioned your system is, how ill-conditioned your matrix is. We look into an example. I suggest that we should look into this example today, just that you get that thrilling example concerning this class. I will give you an example of a matrix condition, and I will show that matrix is ill-conditioned by giving different values. Okay. We saw in the class today one example of ill-conditioned, right? Isn't it? Crossing each other are very parallel to each other, but not parallel, but very close value of slope. So we were not able to identify the intersection points. Okay. Maybe this also I did not cover in this class. Maybe I should not tell this. Matrix is diagonally dominant or not. Okay. So maybe let me not tell you this. Why I know don't need to tell you this is because this will be coming ahead in a type of iterative method we will be learning. Okay. Let us see that, then I will come here explaining what is this diagonally dominant matrix. Now the iterative process we will be dealing in this class, okay, will only converge to a solution if your matrix is diagonally dominant. That is a theorem, there is a proof, but we just know this stuff that if your matrix is diagonally dominant, then your method converges. So then we will be looking into this code of Gauss-Seidel. Yeah, and solve this equation. Yeah, maybe this one I can cover, right? Yeah. Moreover, in today's course, like in today's lecture, right? You spent a lot of time and effort. You spent a lot of time and effort into computing Ax equal to B form of function and finding x. Okay, via Gauss elimination and Gauss Jordan method. Now, I will tell you that in Python you can just do it within one line. Okay. So, but anyway, that the motivation was for you to understand the process behind. Let us see. This is the matrix A for you, and this is the matrix Y. So we are basically solving A times the vector x equals to the vector Y. Clear? Clear? Are we on the same page? So what we are trying to solve? So yeah. Yeah, so we are basically trying to solve Ax equals to Y. So this is given to you in the code. This is given to you in the code. Our job is to find x. Fine. So let us see. So you can see over here, A matrix is given, Y vector is given. Now x is equal to np dot linalg dot solve. A and Y dot solve command. You just give the input A and Y. A, the coefficient matrix, Y is the right hand side vector of the equal to sign. Okay, if you just give, it is giving you the solution over here. Fine. So what you can do is maybe you can change this code to the examples you have considered in the class today and make yourself convenient that the solutions you are getting is exactly the same what Python is giving. Did you get the question? So this thing I will suddenly randomly check next class. Okay. Next class I will ask you to open the laptop and this notebook should be there with different examples considered in the class today. We solved in the class Ax equal to B today, right? So different examples I have considered, which you did by hand. I want you to use this code and solve command to make sure that whatever you did manually is exactly the same you got using Python. Fine. So here I am showing via Python how to compute, how to get the solution to the matrix equation Ax equal to B. This is one such solution. Let us move into the next. Some of you, I think, Mr. Ankit, Mr. Ankit, he told while I was explaining on the board that Ux equal to P, then you told x equal to U inverse P, right? So that is also type of solution, but computing inverse might be tricky. Okay, so same thing we are seeing here, another method here over here. You can see you wrote Ax equal to B, right? Ax equal to B. How our job is to find what is x. That is you can do by A inverse B. Okay, A inverse B. But manually we are not, we are avoiding it. Manually we are avoiding it because manually computing the inverse is hard. Manually computing inverse is hard. But computation, then yes, you can use it. You can see A inverse is the matrix I am defining over here. That is np dot linalg dot inv function and A. Okay. So I just have to multiply it with the right hand side, y, Ax equal to y. So A inverse y, if I do, I will get x. Okay with you? Okay with you? So it's just giving the x. You see from both the methods. First method I told you is a different method from the one in the second one. And you are getting the same answer. This answer and this answer is the same. So the x vector is the same. Solution vector is the same. Are you able to get the idea what I am trying to do? So in this part, I'm trying to show you that there are different methods to solve linear algebra problem of simultaneous equation Ax equal to B. Okay, one is the Gauss elimination method, Gauss-Jordan method, LU decomposition method. Three methods we learned in the class today to solve simultaneous linear equations. And now we are looking into the fourth and fifth method also using Python. Okay, so this is the fourth method. You saw it here using the solve function. Using the solve function of Python. If you use the solve function of Python, the input it takes is A, the coefficient matrix, and Y, the right hand side matrix of the equal to sign. Then you get the solution directly using the solve function. Using the inverse function also you can compute x equal to A inverse Y. So A inverse times Y. So same solution you are getting. Okay. Now let us come to the LU method, which many of you worked hard during lunchtime. Okay. So we'll see that for any matrix A, we learned in the class, in the morning class, that LU decomposition is not unique. That means you have for the same matrix A, you have different of L and U giving the same matrix A. I'll give you one example also. So you have to import LU from SciPy. SciPy has this LU function over there. So you can call that LU function and LUA. If you want to decompose, LU decompose a matrix A, then you have to import it from scipy.li and ALG. Fine. Then just use LU and A. LU bracket, the input should be the matrix A, whom you want to consider the decomposition. Then suddenly you will see it gives us three outputs. Three outputs, not two. It gives us three outputs. What are the outputs? One is P, one is L, what is U? Can you see that? PLU equals to LUA. So what is this about? L and U already know. Is this a lower triangular matrix? Can you see and appreciate that this is a lower triangular matrix? Because see, also solved it. He also solved it using last. Yeah. Which method is used? Python has solved this. You gave a matrix A, Python gave you the L matrix and U matrix. But through this method, you can easily identify which type of method Python used. What kind of method is it? Just by looking into L and U form, can you tell me what kind of decomposition technique he used? See, Python must also face that problem, right? 12 equation, sorry, 9 equations, 12 unknowns. While doing the LU decomposition, we faced an issue that 12 equation and 9 unknowns were there. Python must also have faced it. Okay. So how Python solved it? Who told you? Is anyone told? No, you told yourself, right? So this is a Doolittle method. How it is a Doolittle method? I am arguing. I am arguing it's a Doolittle method because are the diagonal elements of our upper triangular matrix 1? Since all the lower triangular elements are 1, it is a Doolittle method. So Python is using indirectly Doolittle method to compute it. And then it's not a coincidence. It's not a coincidence that all of your lower triangular elements in the diagram. It's not a coincidence. Okay. So you can appreciate that the method you learned today, that is Doolittle and Kraut method, Python is using it internally to solve it. I hope you appreciate it. Okay. But yes, L and U, this is upper triangular matrix. You can see all the lower below the diagonal, 0, 0, 0, below the main diagonal, all are 0. And LU is giving back the same matrix which you have typed here, which is A here. Where is A? Yeah, A is this one. So you're getting exactly the A quantity. Okay, fine. Now, what is the matrix P? P. What is matrix P? Like when you do the LU decomposition, a P is automatically returned. Can you say what is this P? This might be unknown to many of you. P is known as a permutation matrix. Okay, but why when you do LU function over a matrix A, it is giving you a permutation matrix as output. I strongly suggest you to search a bit about this. Okay, search the function LU in Python. Okay, in your documentation, you can search the documentation of LU in Python, and there it will tell you that P gives you three output. One is L, one is U, another is P. What is the P? P is a permutation matrix, but why it is there? Next class I will ask you randomly. Okay. So next class, what I gave the assignment? Pen? Yeah. So next class I said that I will look into the Python codes. Okay. Python codes for the examples considered in the class. Okay. For the Gauss elimination. And second is what is P as output in your LU decomposition. Okay. So these two will be the just the class assignment. Okay. I need to look into this. Yeah. What you suggest? So I strongly recommend that you search what is P. Hmm? Like just get to know how this works. Hmm? But why we need it here? Here, P is permutation matrix. But why we need it? Why it is giving you as output in the LU? So give some time to it. Give some time to it. Try to understand why you need P. Why you need P? You can search over internet. Okay. Why you need P? Hmm? Okay. So yeah. So that's all done. Take this equation. So this equation just solve. Can you solve and give me the values of x1 and x2? Whatever method you can use, you can use. So a good thing for you is class 16th. I won't be here. Good thing. But to be there, then in one class we are leaving it out, right? So what I suggest is next Monday, can we have this part also? I can take. What you suggest? Then, you know, 16 and 23. I'm not taking. So it will be off. So can we have? So you next week Monday, in the sense that you will have 9 to 12. Sorry, 9 to 12. Break. You can take this break. You can take. So we come to that. 1 hour class is done. Then get 15 break. 10:15 to 11:15 one class. 11:15 to 11:15 break. 11:30 to 12:30 one class. Then 12:15 to 12:30 break. Right. Then lunch. Okay. Then you start at 1:30. One. But I won't take class of 16. You that is it okay for you to take it on that day? Or it will be too hard? 4 hours. Some are saying 2 hours. Then I will take it on Monday. Instead of 3 hours, maybe 1 hour 30 minutes. 1 hour 30 minutes is fine, right? Before that. Okay. Right? No, no. That's what I'm asking you. Or maybe you can tell me some other time. So what I'm telling you is, what I'm suggesting you is, I need some extra time, like around 1 hour 30 minutes. Asking 1 hour 30 minutes. Sorry. Then, oh, finish, finish. Science, how the brain will be acting. But anyway, my idea was to give you any motivation particular for these lectures. Don't worry if you don't understand part. These are lectures recorded, it will be uploaded on YouTube. And I will know how many students are watching it. Video. Please, I suggest you please watch. Don't wait it till the end. I did it for the last semester. Also, waited that then what happens? 20 lectures, each is around 2 hours. Yes. 8 hours videos. Anyway, let us be back. Please think, please think. Class coordinator, please think. So, can you tell me how to obtain this? What x1 and x2 are you getting? 4, 3. Now another exercise. Instead of 1.1, substitute 1.05 and solve it. That means I am asking you to solve this. Or x1 and x2. Some got 8 and 1. So are you seeing something happening here? Mr. Hari? Very well. Are you feeling new television programs around? Let's see, these are some examples. Plus, you went, you don't need to learn. Next class on student performance. Every class till the end of this course, first bench. Class coordinator, remind you. What is his name? Adil. 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 Mr. Adil. Okay. So, Mr. Adil, you should remind me that he sits in the first bench. Every class. See, please get a bit more serious. Hmm? Okay, so I'm telling you that if you took 1.05, you got 8 and 1. But using just 1.1, you were getting 4 and 3. Come on, like with just minute change, the solution should be changed minutely. Just with 0.05 difference, why your solution drastically changed? So this is one of the best examples of ill-conditioned system. Such kind of systems behave like this if there is a small change in your coefficients. Okay. Most importantly, most importantly, if you see that maybe I can substitute it back to the equation, still work. If you substitute this guy into this equation, see 8 plus 2 into 1 is still returning 10. Okay, 1.1 into 8 plus 2 into 1 is around 8.8 plus 10 point how much? 10.9 is it? Yeah. So some difference is there, but almost getting equal. So these are the best examples of ill system. Okay, where a tiny change in your coefficient matrix is leading to like way different solution outcomes. So x1 equal to 8 and x2 equal to 1 is not the true solution to your original problem. Okay. So it might mislead you believing that your solutions are adequate, while it is not the case. Okay. So I'm giving you an example of this ill-conditioned matrices in this example over here. Okay. And so this is what I wanted to communicate. Okay. Maybe we will look into this in the next class. But what should we do in the next class? What's the plan? I will take the normal class, but 16, 23 you will be free. 23 is a working day, right? 23 is a working day. I'm asking you the extra time so that 20. What times? I think. But what I can do is assign another faculty instead of me. How can I just free one time? No, we will discuss later. We will discuss about scientific writing later. Let us finish the competition. What you suggest? Wait, you see, one for the best way I would tell, best way I would tell is next week Monday. Better I will take that class only, like 9 to 1 or 2. Then some 20. Then I will take 1 or 5 minutes extra. That's finished. 4 p.m. we will finish class. It's done. Maybe some are having problem. Class is too long. It's morning. Then we can split the course. I am not worried about that. So if you want, yes, this week. Maybe. I have a class of third semester. Friday morning or evening, I don't know. Friday I can't be. Because Friday, how many of you are comfortable with next Monday class extra of 1.3 hours? So next week we will have the class. So it will be a longer class, but I hope try to understand some more about linear. Today you did not learn, in fact, any kind of numeric. Next class will be an advanced version of this. So please, you are everything is the Google class. Who is- 17, 21, 25, 29. 27. They did not even come last class. I actually wanted meetings. I got the total number of students for the and one that shared with me. But we should also be that. They just not coming to class, not very bad. You don't even see them. So maybe in the middle of the week, possible.